Hi, I'm Zsolt, and this is joint work with Mankit and Manuel about improving the performance of BFT consensus. Permission blockchains have become more and more popular, and they have brought BFT consensus in the spotlight. Now, what prompted this work is the realization that as opposed to their public counterparts, permission blockchains are already being ran and in the future will be ran increasingly in fast networking environments, which bring novel challenges and also opportunities to BFT consensus. And even though there is very rich related work on making BFT consensus run faster, we have realized that many of these works combine together different optimizations and make implicit assumptions in a way that make it difficult for a systems designer to understand the relative importance of different optimizations in a specific fast networking environment. So what we have set out to do is to study independently what kind of optimizations would work well or would work not so well in a fast networking environment. And to do this, we have designed ModuBFT, which is a modular configurable implementation of PBFT, a seminal consensus algorithm, in a way that allows us to simulate different acceleration options. Before we talk about implementation details, let's just look a little bit at the background. So permission blockchains are mostly deployed by enterprises. They rely on identities and permissions for nodes to enter the network. And in their use cases, they resemble a lot the space that databases are in today. Of course, the blockchain brings the benefit of decentralization of trust. Now, as you are all aware, in permission blockchains, there is no need for expensive proof of work consensus, and more traditional forms of consensus can be used. What is interesting for the context of this work is that these permission blockchains, being enterprise software, are often deployed in environments that are controlled and where the nodes can be chosen specifically. So there are examples of permission blockchains running in regional setups like Alastria in Spain, or some applications around stock exchanges, which are again physically confined. Even if distributed across a little bit larger area, the systems are often run in a cloud or in a multi-cloud deployment where the parties have quite some control on the type of machines they run on and can ensure high bandwidth communication across nodes. So this brings nice opportunities because, of course, in the data centers and in the clouds, there's faster and faster networking available. So as you're all aware, bandwidth are increasing, but at the same time, accelerators are present in abundance. And also the infrastructure itself is becoming smarter, more programmable, just overall faster. So in theory, we are in a very good place. It looks like we should have a lot of opportunities for building faster distributed systems, and specifically for the purpose of this talk, for running BFT consensus with very low latency and very high throughput. To check how this looks in reality, we have run an experiment with a state-of-the-art BFT consensus library on a fast local area network. And as you can see in the results, they are maybe not that positive. So even though the system reaches high throughput, its latency is really spanning a wide spectrum of numbers. And even at the lowest level, it's quite far from the underlying latency of the network, which is just in the microseconds. Now, one might argue that this is only because a large batching size is being used. But even if we use a much smaller batch size like 8, the behavior will be quite similar. Of course, by using a smaller batch size, we will reduce the throughput of the system, which points to this assumption of many of the BFT consensus implementations of using large batch sizes and really optimizing the system for batch-based execution. Now, if we look at the bandwidth usage of this implementation, what we see is that even if at its maximum throughput level, it barely uses 20% of the available bandwidth. So clearly, there must be something limiting the system in reaching a higher throughput and the better bandwidth utilization on fast networks. And what that is the fact that BFT consensus really combines a lot of data movement with computation. So as you can see, the cartoon version of the PBFT protocol down below, it is of course a leader-based protocol which works in rounds with auto communication. So it will involve a lot of data shipping back and forth across nodes. It will rely or it will be sensitive to the latency and bandwidth of the network, but at the same time, it also requires quite a lot of cryptographic computation to sign and verify messages being sent across the nodes. So what we've proposed is an experimental framework that implements PBFT in a modular fashion to allow us to understand the cost of different steps in the protocol and identify ways for optimizing it for the future. We've implemented it in Go, and we've designed a software pipeline with many different parallel steps, and each of these steps having a configurable number of threads. So as you can see, we have separated the different aspects in the protocol. So we have the networking operations separated into a set of threads. We have all the cryptographic operations running again as a different set of threads, and then the core of the protocol, which is the decision making, whether a consensus round has been successful or not, whether a new leader has to be elected, and so on, running again as a separate set of threads. So this allows us to really instrument and measure each specific step, and also to swap out the implementation or the configuration at different points and immediately measure the changes. How inside a node looks like. Let's see how clients interact with the system. So clients will send requests to the leader for ordering in the blockchain sense, or for consensus. And these requests are basically binary objects that we assume are blockchain transactions, but could be really anything else. And then the leader will initiate, will send out the consensus request to the followers, and then the followers or each node will send the response back to the client. So in our implementation, we don't burden the leader with having to wait for or collect the responses from the others. Also, each node contains a log of all the requests that have been submitted, but it does not do, let's say, anything with the data, with this binary object that is being sent to it. It has to be mentioned that we designed the system by default not to use batching, so it does have the capability to batch several client requests together at the leader. And of course, clients themselves can, let's say, simulate or do batching by sending larger binary objects to the leader. But for most of our experiments, we chose to really explore an unbatched execution to be able to expose the true latency of the network and the true latency of the operations that have to be performed. Now, using our framework, we can actually simulate, or we can configure different PBFT variants. So we can run, let's say, the most common considered case where every single message across every node is signed with a private key signature. We can run the more optimized version, for instance, present in the journal version of PBFT, which replaces signatures with message authentication codes across nodes. And then finally, we can even consider a case that is optimized for the domain of permission blockchains, where the nodes themselves would send the responses to the client with a message authentication code, and then on the side, in large batches, compute private key signatures on a large number of values or a large number of transactions, amortizing this way even the cost of that signature. So this would be a way of looking through the spectrum of optimizations that people usually consider for BFT consensus. To simulate using some kind of acceleration, we allow the implementation to be configured with two different crypto ciphers. So one would be RSA 2048, which is the default, and then a weaker one to make signing and verification cheaper. So using this technique, we can pretend as if we would have a hardware accelerator having around 4x improvement on signing and 2.5x improvement on verification on the behavior. So this is consistent with what an FPGA or ASIC-based crypto accelerator would provide. To give you a sneak peek of the results, and of course there's more in the paper, what we've done is we measured the throughput of a consensus group running in a fast local area network with different variants of the protocol and 2 value sizes. So as you can see, using the version where every single message is signed with a private key, the system is compute bound and the throughput is quite low. And as we increase the use of message authentication codes, the throughput will also increase significantly. Now, if we ask the question of how would a hardware accelerator for cryptographic operations change the picture, we can actually see that through our simulation approach. And what is interesting is that as you move up, as you move down in this graph and add more and more domain-specific optimization, hardware acceleration will play a diminishing role in the end-to-end performance. So this is in some sense not unexpected, because in the domain optimized version, we have removed almost all private key signatures. And of course, even if we would accelerate them by a significant factor, it would not impact a lot the end-to-end behavior. Now, what is perhaps interesting here is that this explains why some of the related work on using hardware acceleration for BFT consensus has not perhaps been adopted, because just optimizing the protocol for the application might give you a bigger boost than relying on some fancy hardware. Now, what is interesting in this graph, and again, there's more detail in the paper, is that even with the highest throughput, our system is not quite able to saturate more than 7 gigabits per second at the leader. And of course, there might be better programmers than us who are able to build a little bit more efficient system. But to us, this is a clear indication that there's a limit to the throughput of the software-based system somewhere in the 10 gigabit range. And to go beyond that, we will have to significantly cut the cost of some of the other operations in the protocol. And what are these remaining operations? Well, what we show here is a graph with how the CPU cycles on the leader are spent. And what you can see is that the largest cost is now serialization, deserialization, and hashing of messages, which is in some sense not unexpected, because we have removed most of the private key operations already. So to reach faster networking behavior, what we'll have to do is to find ways to make these operations run more efficient. So how you can do this? Well, for instance, by using a smart network interface card to offload these operations. And interestingly, there is quite some emerging work in the systems and architecture community. So I'm showing a few of these at the bottom of the slides, which look at how we can use a programmable network interface card to offload serialization and deserialization. Even though these works are not necessarily in the context of BFT consensus, the ideas are clearly transferable. Another way forward, which we find very, very exciting, is taking the entire BFT consensus protocol and implementing it in specialized hardware. So this would basically make it lower latency, potentially much higher throughput, and just overall more efficient. And what needs to be highlighted here is that the challenges are actually not so much technical. So we know how to implement such a BFT protocol inside the box. What is really challenging is to understand how such a deployment would work together with the assumptions and the threat models that today's permission blockchains have. So to summarize, in this work, we've built an experimental framework that allows us to quantify the different operations inside the BFT consensus protocol with the goal of understanding how we can make it work on fast networks efficiently. And what we found is that software will likely get us a long way. So 10 gigabits per second line rate BFT consensus is doable in software by using a lot of software pipelining and parallelism. But going further to something like 40 or 100 gigabit rates will almost for sure require some form of specialized hardware accelerator. And we provide 2 examples, but since this is an open source framework, we hope that it will enable others to explore other ideas that we have not thought of. One last thing that has to be mentioned is that, of course, today's permission blockchains might not be able to immediately take advantage of a much faster BFT consensus implementation. And clearly, we will have to invest some additional work in this space and understanding how we can modify permission blockchains to this end. And to plug our own work a little bit, we have looked into one possible modification to how a permission blockchain executes transactions, which then exposes the cost of ordering of consensus and allows for future optimizations to be plugged in. But of course, this is only one idea. So I think there's a lot of discussion still needed in this space, and we hope that after this talk with the questions, we can learn about other directions and other interesting ideas that people have in this space. So thank you for your attention, and we're happy to answer any questions.